Hello, welcome back. In this segment, I will complete the De Morgan's law by proving the converse of the statement that I discussed in the previous segment. Okay, so I need to prove this in this segment. Not P or not Q is same as not of P and Q. Okay, I will be using the proof logic assistant to prove this. So I created this problem already. Not of P or not of Q is same as not of P and Q. We will go ahead and make a proof using case-based reasoning and contradiction. Okay, let's go ahead and create a new subproof. Let's assume not P is true. Let's make an opposite of the conclusion. Okay, the conclusion is a not in the front. I'm going to ignore the not. I'll just say P and Q, and which allows me to deduct P because of and elimination, line number 3. And now I have a contradiction because line number 2 says not P, line number 4 says P. Okay, that means I will get a contradiction. This is due to not elimination of line numbers and 4. Okay, so what it means now is that my internal assumption, right, P and Q must be wrong because that is the one that led me to the contradiction. Okay, that means I need to say not of P and Q because I'm going to do not introduction, line numbers 3 through 5. Okay, let's check the proof. Make sure you are okay. Yeah, I'm going to pause here and think a little bit. So we have the premise. This is the premise. So I'm making this here. I'm going to do case-based reasoning. I'm going to assume not P is true. So this is the not P part. Yeah, it's an assumption. And I'm making a proof by contradiction by just ignoring the not here. So this is the conclusion, by the way. This whole thing is a conclusion, but I'm ignoring the not. So I get only P and Q. From P and Q, I can eliminate using the and elimination rules to obtain a P. But we know already not P is true according to our assumption. That means we get a contradiction. Okay, this contradiction means that this initial assumption that P and Q is the reason why we get a contradiction. That must be wrong. That is the reason I put a not in the front. Okay. So now, if not P is true, right, we are able to come to the conclusion not of P and Q. Okay, let's do the same for not Q be true, and then we can combine. Yeah, that's what we're going to do. Now I will be doing the same, more or less. I will again prove by contradiction by just using P and Q instead of not. This is the conclusion, but I'm negating the conclusion. And now it becomes much easier. Now I just can derive Q because it's just and elimination, line number 8. Okay, but now I can end up in a contradiction because of line numbers 7, 9. Okay, should be same as not of P and Q, which is because of not introduction, line numbers 8 through 10. Okay, now what shall we do? We have a nice structure we can reason about. We have this hypothesis which is made of an OR statement, not P or not Q. If not P was true, we were able to come to the conclusion not of P and Q. Similarly, if not Q was true, we are able to come to the conclusion not of P and Q. So in both cases, we are able to arrive at the same conclusion. This is exactly what we talked about in the OR elimination rule, which we will apply now. This is because of OR elimination, line numbers 1, 2 through 6, 7 through 11. All right, I think we are done. Yeah, congratulations, the proof is correct. That's basically it.